All right, guys, so let's go ahead and get started with today's material. So what we want to do now is to build on last night's video, which was an introduction to the modern quantum mechanical model of the atom, which was developed by Schrödinger and de Broglie. All right, so we gave you a little bit of an overview of the assumptions of the model in the video, but now what we want to do is build out on that. And there are two primary things that we need to discuss here. So when we talk about the modern quantum mechanical model, we have to talk about orbitals, which we sort of loosely introduced and defined in the video at the very end. And we essentially said that an orbital is a three-dimensional region in space where with some degree of statistical probability, we might expect to find one or more electrons. Okay, so we can think of the orbital as being the house for an electron. All right, and then we also have this idea of quantum numbers. And that extends from the quantum number idea that we got from the Bohr model that we talked about last time in class. And essentially now a quantum number is going to represent an individual identifier for every single electron in the atom. And the assumption that we make, which I think we also mentioned in the video, is that every electron in the atom has to have a unique set of quantum numbers. So no two electrons in the atom can have the very same set of quantum numbers. Okay, so it's an individual identifier for every single electron we're talking about. All right, so those are the two things that we have to talk about. Now, when we pull these things together, we can talk about the various sets of quantum numbers that we can actually have for a set of electrons in the atom. Okay, so we're going to talk about them. So it turned out we're going to have four different kinds of quantum numbers that an electron can have, and every electron is going to have a full set of all four. All right, so let's talk about those quantum numbers ranging from the least specific or most general to the most specific. All right, so the first one is what we call the principal quantum number. And the principal quantum number is given the symbol of n. So you'll recognize that because that's the very same n that we used in the Bohr model when we defined the quantum numbers of the various electrons in the orbits of the Bohr atom. So remember in that model, we had a single electron from the hydrogen atom. We could put it in any one of those orbitals, but if it was housed in a particular orbit, we had to give it a quantum number n. And the further out we went from the nucleus, the bigger n got in integer values. And the same thing is true here. So n can take integer values from 1, 2, 3, extending up to whatever. Okay? Now, what does this tell us? Well, it's actually very similar to the quantum number that we used in the Bohr model of the atom. What it defines for us is really two things. The first is the distance of the electron from the nucleus, same as in the Bohr model. And the second thing it's going to define or tell us about is the energy of the electron. Now that was also true in the Bohr model as well. So remember, in the Bohr model, as the electron moved out to farther and farther energy levels or orbits, okay, the distance obviously from the nucleus increased, but the potential energy of the electron also increased. And I gave you an equation for that. That was the one dealing with the Rydberg constant at the very end of class. All right. And another thing that keep in mind here is I sometimes will refer to this as the principal energy level quantum number. All right, so really this is kind of like talking about Bohr orbits, right? So as we move out from one orbit to the next, we can also say we're moving out in terms of what we would call principal energy levels. Okay, so this is really more or less what this quantum number is telling us about. All right, so that's again the most general kind of quantum number that we can talk about. Moving on to a slightly more specific one. The second one is the angular momentum quantum number. Okay, and the angular momentum quantum number has the symbol of a lowercase script L. So that's what that is. Now, it also can take on integer values, and here's what they look like. So L can equal to integer values of 0, 1, 2, 3, and on upwards from there for as many as we need within a given range. Okay, so the range is going to be from 0 to n minus 1. Okay, so L can inhabit that range between 0 and n minus 1. Well, what's the n? N is that principal quantum number. Okay, so in a sense, the principal quantum number dictates the values of L that we can have. All right, now what this actually does is it's going to define for us, now we're getting into the orbitals, the type of orbital or types of orbitals we have. All right, so let me give you an idea of what we're talking about here. I'm going to give you some N and L values, just so we can see how all this works. So remember the values that N can take. It can take integer values starting with 1. So maybe for the first 3 principal energy levels, we could have N equals 1, 2, and 3. Okay, these are, again, kind of like Bohr orbits. Now, what about the L? Now let's take a look at N equals 1. What values of L would be allowed? Okay, so take a look at what our range can be. Okay, so up here it tells me that L can range between 0 and n minus 1. Okay, so what's n minus 1 in this case? N minus 1 in this case is 1 minus 1, which is 0. So there's only one value of L that we can possibly have here, and that's going to be 0 for the n equals 1 level. See how that works from that equation up there that I gave you for the range. Now let's do n equals 2. All right, so let's start with n minus 1. Okay, so that's going to be the upper end of the range. So 2 minus 1 gives us 1, and my allowed values are 0 and 1. Okay, so notice as I go to the n equals 2, I can pick up another L quantum number here, okay, within that limit or range that I gave you above. You can do the same thing for n equals 3. Okay, so take the 3, again, take it up here to n minus 1. So 3 minus 1 is 2. So I can have allowed values of 0, 1, and 2. Okay, everybody see what I did there? All right, so what I'm actually doing is I'm defining a quantum number that goes with a specific type of orbital. Okay, so here's how it all kind of boils down. And you might remember from high school or any other place where you've had some chemistry, kind of the names of these orbitals. You might even remember the various shapes of the orbitals, and that's kind of the next thing we talk about. But if, here are my orbital types, if L is equal to 0, that corresponds to what we call an s orbital. If L is equal to 1, that's what we call a set of p orbitals, or we can say it's a p orbital. We're going to find out there are different ones. That's the next quantum number we have to deal with. If L is equal to 2, in that case, what we have are a set of what we call d orbitals. And then if I have L equals 3, that corresponds to what we call a set of f orbitals. Okay, so notice that the L quantum number tells us the type of orbital that we've got. And that's important because remember, we've got to put electrons in there. Okay, so this is kind of telling me which house a given electron is going to go into. All right, everybody okay with that so far? And it's going to make a lot more sense when we sort of put it all together, hopefully. So far, so good? All right, so let's go to the third quantum number. And again, remember, as we move upwards here in quantum number, we're getting more and more specific about the actual address and type of electron we're dealing with. Okay, so the third one is actually called the magnetic quantum number. And we're going to give it the symbol of lowercase m sub lowercase l, m sub l. All right, so again, like any other quantum number, what values can it have? It's going to be able to have a range of values. So m sub l turns out to be equal to, or can take a range of 0 plus or minus 1. So now we can have a negative quantum number, plus or minus 2, plus or minus 3, on out as far as we need to go within this range. Negative L is less than or equal to m sub L, which is less than or equal to positive L. Okay, so you'll see how this works in just a second here. Now, first of all, what does this quantum number tell us? What it's doing is it's telling us the different types of orbitals within a given set of orbitals I can have. So in other words, remember, I only have one kind of s orbital, but remember when I get to the p's, I can have different ones in there, okay? So this is telling me the different types of p orbitals I might have, or the different types of d orbitals or f orbitals I can have within a given type of or within a given type of orbital. So what it's really defining is kind of the orientation of the orbitals in space within a given type. This will make more sense when we start drawing them out. And when I say in space here, I mean in three-dimensional space as we draw them. Okay, so let's take a look at what I'm talking about here. So again, kind of working from n through l to m sub l here. So let's look at n's, let's look at l's, and let's look at m sub l. So we're just kind of building out that chart that we started before. If my n is equal to 0, okay, let's work our way down. We found out that if n is equal to 0, L also has to be equal to 0, right? Or sorry, n has to be 1. Sorry about that. I can't have a 0 for n. Okay, so n is equal to 1, L is equal to 0. We did that just above, right? So now, what options do I have for m sub l here? Well, go back up here. M sub l is limited as minus L is less than or equal to m sub l, which is less than or equal to L. Okay, so if I have an L equals 0, I've only got one option for m sub L. That's also going to be a 0, right? That's the only thing that can lie within that range. Okay, so now I'm just going to put a little divider here. So now let's say that I have n equals 2. Okay, so remember, what L values can I have? Well, I can have L values of 0 and 1, right? Those are my values of L, remember? They go as n minus 0 up through n minus 1. So now let's go downwards here and see what options I've got for m sub L. Now, if I'm at 0, okay, I only really have one option here for m sub L, and that's also 0. So that one kind of derives from there. But what if I have an L equals 1? What does that tell me? Well, that means I can go from minus 1 all the way up to 1. Right? So that means I've got minus 1, 0, and 1. Okay, so basically, I get 3 options for an L equals 1 from my range equation up there. Okay, so that takes care of n equals 2. Now, what if we go out to n equals 3? Now, what are my various options I have there for L? Remember, it's n minus 1, 0 to n minus 1. So it looks like I'm going to have 0, 1, and 2 as my options there. Okay, those are my options for L. Now let's look at my options for m sub L underneath each one of those. Okay, so the 0 is obvious. We've done that one before, so I have a 0 there. The 1 we've done, so I have a minus 1, a 0, and a positive 1. So that goes there, there, and there. But now, if I have 2, what are my options? It's minus 2 up to 2, right? So let's take a look at what we would have. We'd have a minus 2, a minus 1, a 0, a positive 1, and a positive 2, wouldn't we? And all of those stem from my L equals 2. And again, it comes from that equation right up there, okay, or that limit, if you will. All right. So what's this actually telling me? Well, again, it's kind of telling me about orbitals, right? So if I drop this down, if I have an L equals 1, remember that's an s orbital. And what I'm telling you here is in the n equals 1 level, I can only have one s orbital in there, right? Now, if I go to n equals 2, okay, L is still 0 coming down. That's still an s orbital. But now if I go to L equals 1, okay, that's a different kind of orbital, isn't it? It tells me that's a p orbital, right? So I'll put p down here. But now what is it telling me about the p orbitals? Oh, it's telling me I have 3 different ones there. I have 3 different options of p orbitals within a given principal energy level. Okay, so now let's go to n equals 3. Okay, L equals 0, that's still an S. Okay, if L equals 1, that's a set of p's. 3 different ones, right? But now if I go to L equals 2, remember that is a set of d's. And if you look at this, how many different kinds of d orbitals can I have within a given principal energy level? Count them up. 1, 2, 3, 4, 5 of them. Okay. And if I went out and picked up another set of f orbitals, say in the n equals 4 level, you can kind of look at this. I have 1 type of s orbital, and I go to 3 types of p orbitals, 5 types of d orbitals. How many different kinds of f orbitals do you think I would get? 1, 3, 5. What should be next?
7.
7. Yeah, so you have 7 different f orbitals. Very good. And the other thing you're going to note is where's the first principal energy level or n value where you pick up a set of f orbitals? Because again, notice the trend. Whenever I go from one principal energy level to the next one to the next one, n equals 1 to 2 to 3, what am I doing? I'm picking up a new set of orbitals, aren't I? Okay, so if I go to n equals 4, am I going to have f orbitals there? Yeah,
Yes.
I sure will. And then if I go out to n equals 5, I'll pick up even a new set of orbitals, which we would call g orbitals. And then by definition, you could tell me, for example, how many different ones of them you would have. Okay. But generally speaking, for ground state atoms that we're going to be talking about, we don't ever have to use g orbitals. Really, as far out as we have to go are the f's. So that's really as far as we worry about. Okay. Now, there's one other kind of quantum number that is the most specific kind of quantum number, and it's actually, fortunately, an easy one to deal with. And it's what we call the spin quantum number. Okay, and I'm going to call that an m sub s, lowercase m sub s. Okay, so here's the deal. A couple of rules we have to think about when we understand the spin orbital. The first one, and I might have mentioned this in the video, or maybe I didn't, but each orbital, each kind of orbital can only hold up to 2 electrons. All right. Now, if I put 2 electrons in an orbital, let's say in an s orbital, they have to be differentiated, right? Because remember, the original rule is that every single electron has to have a unique set of quantum numbers. Now, if you look at it in terms of the little graph I've done here, this little table I did, okay, if I put 2 electrons in any one of these orbitals, okay, the problem is they would have the same quantum numbers up through n sub L if they were inhabiting the same orbital. But I need to now differentiate within an orbital. So that's what the spin quantum number does. So I can define my m sub s as taking values of plus or minus 1/2. There's only 2 options here. And that's all I need, right? Because if I can only put 2 electrons in an orbital, I need to tell the difference between those 2, which means I just have to have 2 quantum numbers to do that. So the plus or minus 1/2 would do that. So what does it define? What actually defines the direction of the spin of the electron in the orbital? All right, so what do I mean by that? Well, you can think of an electron as actually spinning like a spinning top would. Okay, so if you think about a top that spins, it only has two options. It can spin either clockwise or counterclockwise. So that's what I mean by the direction of the spin. We can think of the electron as either spinning around on an axis clockwise or counterclockwise. Those are the two options I've got. So one of the quantum numbers corresponds to clockwise, one of the quantum numbers corresponds to counterclockwise. All right, so that's really all that's happening there. So you can see now that once I've defined all these different quantum numbers from most general to most specific, with the most specific one being the m sub s or the spin quantum number, now I'm in a position where I can assign every single electron that I have in an atom a unique set of quantum numbers. Now, the other thing I want to do before we call it a day here is I want to talk a little bit about orbital shapes and types. Okay, so for example, remember we can define an orbital by its angular momentum quantum number, or L. Okay, so if L is equal to 0, we said that is an s orbital, right? So what does an s orbital look like? Well, what we have to do is think in terms of Cartesian coordinates, right? So three-dimensional coordinates. So I can have an x, I can have a y, and I can have a z-axis that goes in and out of the plane of my paper here. And what an s orbital looks like is a sphere. So this is kind of the one that we talked about in the video, okay, as an introduction. All right. Now, what about L equals 1? Well, that's where I would have a set of p orbitals. How many different kinds of p orbitals could I have? I could have 3 different p orbitals as defined by the m sub L quantum number. Okay, so what do they look like? I'm just going to do 2 sets of axes here. So I can have a situation where a p orbital radiates 2 lobes along the x-axis like this. So it kind of looks like a dumbbell. Okay, and I would call that a p sub x orbital because it radiates out along the x-axis. And you can kind of see what the options would be. I could have an x and I could have a y. Okay, so I could have another set that looks the same way, but now radiating along the y-axis. I'd call that a p sub y. Okay, and then I could also have the option, and I'm just going to swap my axes here. I could have an x here and a z here, and now just for the sake of reference, y goes that way. So I could actually have an orbital running out along the z-axis like that, and I would call that a p sub z. Okay, so remember, for L equals 1, I have 3 different options. Those are the 3 different options. And notice how we're defining here by type of orbital or quantum number within not SL, it's the magnetic quantum number. Okay, how the orbital is defined in terms of its orientation in space. And then I'll just show you a set of D orbitals just to give you an idea of what those look like. We won't do S. So remember, with the d orbitals, there are going to be 5 different ones, right? So let's draw 5 sets of axes here. So I can do an x and a y, and I'm just going to flip some axes here because these ones all kind of look the same. I'll do an x and a z, and I'll do a y and a z. Okay, so here's what they look like. They kind of look like 4-petaled flowers where the petals kind of bisect the axes. This one's going to be called a d sub xy because the lobes actually bisect the xy axes. And notice here I flipped my axes in the second one. So it's going to be the same kind of thing. So in that sense, they're like p orbitals. They look the same, but their orientation in space is different. But now we're bisecting the xz axes. So I would call this one a d sub xz. And then we have the yz axes, same thing. Put them out here as lobes. And since these guys actually bisect the yz axis, I'll call that a d sub yz. But then I got two more, so they're going to be a little different from each other. So I'm going to draw two different sets of Cartesian coordinates down here. This will be an X and a Y. And these ones look the same, but now they look kind of like p orbitals in the sense that they go right along the axes as opposed to bisecting them. And for some reason, which I can't tell you, this one's called a dx squared minus y squared. It's just like a name we'll give it, just like we call it Sam or Bob or something. And then there's one other one, which I think is actually really interesting. Let that be the X, we'll let that be the Z. Now Y is coming in and out at you. Looks like a p orbital radiating along the Z axis, so it looks like a p sub Z. But now the difference is it has around the girth of it, if you will, sort of a donut of shape or electron density about it. And we'll call that one a d sub Z squared. Okay, so there's your 5 different d orbitals. And again, you could do the f orbitals if you want, but they're going to get even more complicated, and they're going to be 2 more of them. You end up with, I think, another set of lobes that you have to deal with. So they get really hard to draw. Okay, so that's why we don't do F's and G's, because they're just really hard and complicated to draw. All right, but that's essentially what we're talking about here. So what we want to do in the next video, which you guys are going to watch over the weekend, is with all these quantum numbers and orbitals in mind, now the big question becomes, how do we actually fill them with electrons? There has to be an order in which we do it. Okay, so what we want to define in this next video is what that order will actually look like. So what we'll do on Monday is we'll come back, introduce that concept, and we'll play with some practice with regard to this kind of stuff and also what we're going to do in the video. And this stuff is actually fairly easy to do once you get your jaws into it. So we're getting away from mathematical stuff, and we're talking really about more conceptual stuff here, which honestly a lot of students find easier. And that's kind of how the course is going to go pretty much for the rest of it. All right, guys, so we'll practice some more with that on Monday, and we'll get about 2 videos worth of practice in since we didn't get some in today. All right, have a great weekend, everybody, and I will see you on Monday.
Professor, I'm just making sure that you remembered about me missing last.
Yes, I did.
Friday.
You're Mr.
Okay,
Rolls,
yep.
right?
I was just making sure.
Yep, I remembered. Thank you for reminding me, but I did remember.
Okay, that works. Have a good weekend.
All right, you too.